Hi, Carlos.
Bastian, how are you?
I'm fine, thank you. Can you hear me? Yes.
Can you hear me?
Yes, I can hear you.
Okay, good, thanks. How's everything?
It's very warm now.
It's what?
It's very warm.
Oh,
Uh,
yeah, so it's starting already? Okay.
Summer is coming, yes.
Yeah, it's still early, no? It's usual to be that warm now already?
In September in Santiago, I would say it is normal, of course. So we'll wait for the audience to join us. Just a few minutes.
Sure. Should I test the screen share? See how it goes.
Yes. Yes.
Uh, what is, do you see now something?
Yes, perfect. Yes.
It's the big yellow thing, or is it the presenter mode? It's good.
No, yeah, it's the yellow slide.
Hey Carlos,
Hello,
this is
Omar.
this is Omar.
Hi.
I haven't met you in person. I've seen your picture online, but yeah.
I hope it's a good picture.
No, you look better in person, actually. Yeah. Yeah. No, very excited to hear about this impressive stuff you've done in the last couple of years. So
Yeah,
yeah,
there's
good
some,
stuff. Good stuff. Yeah.
yeah, thanks. Since it's a seminar like with students and everything, I also put some ongoing ideas or ongoing work that is not yet finished, which, usually also helps inspiring the students that, there's work to be
Brilliant.
done.
Yeah.
Some
Even
things are
better.
on.
Yeah. Yeah.
Yeah, let's see.
Cool.
So Carlos Omar is who introduced me to this model-based and model-free literature and neuroscience things.
Yeah, so I see. Yeah, I had also, it was the same for me. I had a friend of mine working with Peter Bayan back in the UK. So he's a neuroscientist in Lisbon, and he was the one that
Introduce you to the. What's his name?
Bruno
Bruno.
Miranda.
From Miranda. Yeah. Yeah. From Portugal, I know Rui Costa.
Mm.
He's done stuff similar to mine. Yeah, I think that's the only Portuguese I know, actually. Yeah. Well, I also worked with this postdoc in Cambridge, Paula Banca,
Also Portuguese. Yeah.
the Portuguese as well. Yeah, those are two. Yeah, but yeah, I did economics and mathematics first. Then I moved to psychology, and then I also met Peter Dayan at some point, and all these guys that are super influential in the
this,
field.
yeah,
Uh,
exactly.
But I was trained by Dickinson, who's the guy who in rats
I know.
discovered this distinction between habits and goal directedness. So I'm all over the
Big
place,
name.
but cool stuff. Yeah. Yeah. And then I taught what took me like 5 years to Bastian, and he picked it up in 6 months. Took it from there.
And then it's good that you are here, because then I'll have a slide that I'll hand over to you to present it if you want, with the two-step task.
We did two-step task. Yeah.
But it's
Cool.
it's basically for me to give an overall idea about what we can do with it.
Yeah.
And
Cool.
and I know you and Bastian have done some work with it. So
Yeah, we introduced that task into the transportation community, actually.
yeah.
And
The way
I can
yes.
say that with confidence, because the first time we submitted the paper, we got reviews, 2-line reviews, in which the guys were basically, we don't really understand what's going on here. So the editor had to reject the paper for lack of information, basically. And but then, yeah.
But it was nice because I know the paper that you're referring to, and you actually adjusted the two-step task or the standard one for the particular transportation.
Exactly. Inspired in this paper in economics, forced exploration paper in which they found that people that were forced to explore after a strike in the London tube found better routes. So then that led Bastian and I to realize that it was maybe that these guys were sub-exploring better alternatives by being habitual in their commuting behavior. So
there is a big paper, a very famous paper also on the twin. It's an old paper, but not on the modeling, but on this particular aspect on the twin cities. I always forget the name of the two cities in the US that are called the twin cities. It's what is it?
Is it Michigan or no?
Yes, Minneapolis and yes. Yeah. Anyway, there was basically a bridge that collapsed. And so here it was a route choice problem. And so you could see they had sensors on the network that would measure the flows of people going from different areas in the city. And it was kind of stable. You have the seasonal trends. See that it's stable. And then suddenly there is, and they had to cross. So basically you could measure because there's a river and there's only a few places where you can cross. Right? And so they could see exactly where people were crossing and which routes they were taking from area to a different area. And then suddenly a bridge collapsed. And for a certain time, they basically had that alternative was no longer offered. So a lot of people that was going through that bridge had to go somewhere else. And the interesting thing was afterwards, they built a new bridge on the same place. And you could observe this, these things over months because they were basically collecting the data on the field, not on the individuals, but collectively then after the drop, then it never went back to the previous state for the whole system because a lot of people basically learn new routes by the fact that they're forced to do so. But then,
that's basically the same result, actually. It's exactly the same. I don't think we cited that paper, did we? Yeah. Did we cite that paper, Bastian, in that? I don't think we did. I don't think we did, actually.
I didn't know that.
Sorry, yeah.
No. It's a famous one from the US, but no, I mean, it's mostly on the learning new routes. There was no kind of theoretical ground to argue for what was going on from
I see.
By the model 3. It was just
Sorry, I have to interrupt you. I think we should start. I know, Carlos, it's okay, yes?
Yeah, sure. Can I start?
Yeah.
So let me first introduce Carlos. So we have a small audience. So, Carlos is an associate professor at the Department of Technology, Management and Economics of the Technical University of Denmark and a research affiliate at the ITS lab at the MIT. He has a Bachelor in Science in Structural Engineering, a Master of Science in Transportation Engineering, and a PhD in Transportation Systems, all from the University of Lisbon. So, Carlos, you have like 30 minutes, and we have some time for questions. So the stage is yours.
Thank you. And thanks for the introduction, Bastian. Yeah, I'm in an unusual setting here in Denmark. I'm in the Department for Technology Management and Economics. So I get very happy when I'm asked to present in a civil engineering department, because as you mentioned, I'm a civil engineer. And so it reminds me where I belong somehow. And I did a PhD in transportation where I worked a lot already with behavior modeling, but mostly driving behavior. And I was very interested in computational methods, so did a lot of simulation work and tried to use simulators to predict accidents and safety. And so looking at behavior and how you simulate those in terms of driving. Before that, I was a structural engineer and worked as I would say the core in civil engineering a long time ago. Then I started to get interested in activity-based models from behavioral perspective, and worked on how these can be used for studying new technologies. And that's still in my core, and I'm not going to talk about it today. I'm just saying that to explain a bit some of the things I will say in the presentation. It depends on this work that I did in the past. Then at MIT, I worked a lot in demand management strategy, mostly on designing incentives and tradable credit schemes for more efficient and more sustainable systems, but with a clear focus on designing these models using choice models and how we can use technology to learn behavior. So tracking people down with smartphone apps and build choice models from it. And I'll talk about this in a bit as well. And here at DTU, I'm in a group called Machine Learning for Smart Mobility. Well, it has been changing some names, but at least it's where you want to go. So here are the pictures of our group, which is a very nice group. In case any of you want to spend some time, you can ask Bastian about it. He was here with us for some time. And so we are a group of people from traditional transportation modeling techniques and machine learning, and we try to combine both. And I've been focusing in this presentation on how we combine choice models and emotions with machine learning and with a clear aspect on how can we collect data that can be used for these kind of models. So that's it. So I'll a brief outline. I'll give a bit of context, and then I have these kind of question marks to show how we are trying to motivate some of our studies. So how do we experience mobility? How can we measure emotions? Can we explain emotions? And can we explain emotional patterns? So when we look at temporal changes, and then how do emotions affect decision making? So the other way around. If you think about all the previous questions are basically we do things in mobility, in travel choices and travel behavior, and we have an outcome and we have some experience that will affect our emotions, but we have the other way back where emotions affect the choices. So we look a little bit about it, and that's where we haven't done much, but I'll start to explain what we hope to make a change, and then some ideas about where we are working now. So when I was probably in high school, I remember that I was shown this picture with areas of the brain, right? And these are lobes where people say, okay, this is the region that the prefrontal cortex, which is the front part of the brain, which is basically what makes decisions. And this was actually an image that I took from a presentation from Hani Mamasani. He passed away this year, but he had this slide in his lifetime lecture earlier this summer. And this was kind of identified as the region where people have this evaluation of rewards and where choice preferences had an impact on the activity of the brain. So every time there was a choice to be made, then this part of the activity or this part of the brain was being activated. And interestingly, the way economists formulated the choice behavior a long time ago was through a formulation of some sort of scoring function, what we call utility, that tries to compute somehow a relationship with these rewards. And of course, when computing these utilities, they're formulated in a linear way, and most of you probably know that is a common standard of transportation community to build these decision models, where you have a coefficient beta for the preferences. So basically, you had explicitly, in a simple way, to formulate rewards, individual preferences, and then the probability of a choice, right? So the economists proposed this a long time ago. It was nice to see that actually what happens in our brain has some linkage to this formulation. But interestingly, there are other things that are related to decision making. And when our neuroscientist friends looked at what happens when people are faced with decision, they've noticed that other parts of the brain are associated with this whole process. And so it's quite famous now, the reward system. And maybe some of you have heard about dopamine and how it is linked to this reward system. But basically, there are other parts of the brain that are linked to this decision process. One of them is how you acquire or elicit the response. So the learning component, which is a different area of the brain called the striatum. And in the other side, you have the ventral tegmental area, where you have the stimulus for the rewards and the production of dopamine in the brain that then generates back the process of the rewards evaluation affecting the choice decision making. And along with it, there are other aspects on areas of the brain that are clearly related to the contextual memories and eventually attitudes and what build your, let's say, strong contextual process for decision making, which is the hippocampus. And then you have another area which is called amygdala, which is often related to traumas or emotional memories, both positive and negative. And all of these areas of the brain are triggered through a decision process, through the reward system in the decision process. So then it shows that, you know, the classical formulation, why am I talking about this? It's not nothing that we use a lot in transportation, but it shows clearly how there is these processes that affect decision-making beyond preferences and beyond the attributes and beyond this utility process and utility maximization. And there, of course, you know, we know that, and some people working in choice modeling have worked with that, but the mechanisms on how these different processes can be modeled, it's still an open question. So that's the motivation of today, and the context is basically how can we measure and model experiences together with choices, but focusing on this context, the learning, and actually the rewards and the experiences together with the choice preferences, the reward evaluation. And ultimately, what drives me, it's of course, I'm interested in understanding more about these choices, but there is a link between all these dimensions with health effects. So whatever your emotions or experiences, there's a clear influence on the outcomes that are not just the decision-making process, but on your health. And I'm not going to talk about it this time because it's something that we haven't worked a lot, and I'm not a health expert, but it's something that motivates why we should look at these things a bit more into detail. So how do we experience mobility? So here I'll rely on a particular project that we've worked on the last 5 years. And the idea was a group of people from these universities that you see here at the bottom got together the idea that can we try to find and show this empirical evidence that urban features affect mental well-being and your emotions and mental well-being. So we designed a set of different experiments from very controlled to very uncontrolled to see if people, when they are faced with different features of the urban environment, how do they affect emotions? And so there was and I'll talk about another experiment, 2 experiments today, mostly one and a second, but it started by, you know, having people in an fMRI looking at videos of first-person walks in different urban environments. Experiment 2 was a similar experiment, but instead of being in a fMRI, you are basically with an EEG and looking at videos of different neighborhoods. You had experiment number 4, which is an outdoor experiment, 3 and 4. Experiment number 4, you basically had people that had to walk the same neighborhoods that were shown in the video, but now they actually had to go to these neighborhoods outdoors with outdoor equipment that measuring where you're looking with eye tracking, recording your sound, but also doing scans with the EEG on your brain. Experiment 3, it's the one I'm going to talk a lot about today, was basically a very uncontrolled experiment where we only had physiological measurements from a wristband, but we asked a lot of things about what people are doing to understand the context and the activities and the trips that they were doing through a mobile phone. And experiment 5 was a bit of a more intervention where we said, okay, let's put with the same equipment that people used in experiment 4, but let's put them in a VR environment where we can play around with, for example, the textures of the buildings, the greenery that we have in the streets, and see if people have, mostly focusing on navigation and people with mild cognitive impairment if they were able to locate themselves in this virtual environment in the same way. So there's a lot of things that we collected lots of data, we find interesting things, but I'll talk mostly about experiment 3. And in experiment 3, here what we did was basically having these two technologies. One, it was a standard medical device that has been validated for a lot of clinical experiments that measures the heart rate, the electrodermal activity, skin temperature, and has an accelerometer. And also we asked people to install a smartphone app on their phone, which is a travel diary, with some additional, let's say, modifications, the mods that we did to the app to ask them how they were feeling randomly during the day, but also in retrospective at the end of the day. So we would ask 3 times a day, how do you feel now? And they would answer maybe right away or a few moments later, and we could record when they answer. And we had these standard questions on the dimensions of arousal and violence. I'll mention in a bit on how they are feeling, how calm they are, how stressful they are, and so on. But we also ask in retrospective, at the end of the day, when they are basically validating that all the trips and activities that they performed that day, they would tell us also how they felt during a particular activity earlier that day, with whom they were, and give also some other context that I'll mention. So the advantage of relying on the smartphone data is that you then can, of course, have geolocated data and extract even further data about the locations where these people were doing activities and visits. So we could then go to a particular activity and extract features from OpenStreetMaps and from Mapillary, which is, let's say, an open source Google Street View, about all the images around that particular point and try to describe that location, right? So we did this experiment both in Copenhagen and in Lisbon. And of course, with a relatively small sample for when comparing to standard surveys, but of course, a relatively larger sample when compared to neuroscience experiments in controlled environments. And of course, we asked them to wear this equipment for 10 days to 2 weeks in their daily lives, where they would only stop collecting data during their sleep time when they were sleeping. So what can you get with this type of data? So here's an example. So here we are looking at heart rate, which is something familiar to most of individuals. And this is data for a particular subject in Denmark. So she's a female, 40 years old. She's graduate, she works, she has a decent salary for Denmark. She lives in a household with 3 other people in the central area of Copenhagen. And here it's basically data for 4 days, where you have in the x-axis you have time, and in the y-axis you have the heart rate. And what you see here is the different activities that she's doing in each of the 4 days. And you can see, first of all, and we know that from activity participations and travel diaries, that you have a lot of variability of what the person does in a single day. It's not every day the same. Some people do have regular commute and that's it, but there's always additional activities that you perform during the day. So here you can see that, for example, that she takes the bike inside the train, which is allowed here in Denmark. And then she starts work around 8 a.m. and she stays at work until 3 p.m. in the afternoon. Then again takes the bike to the train, and then has a shopping activity before going home, for example. And on a Friday, which I call here, so on day number 2, there's an activity of working out, which I didn't put, I think the label is not here, it's missing. But then in the 3rd day, you have an ideal Friday where she only worked for a few hours in the morning and then has a bunch of errands from staying at home, eating out at dinner, and do a shopping late at night, or in the evening, not late at night. And then in a weekend, you can see that then the activity is very different, with a lot of activity with the kids of drop-off, accompany, drop-off, or pick up someone else. And then you can now have these mobility patterns together with physiological data. And you can see that there is a lot of variability from the heart rate as well, which, it's probably associated with some physical activity. But the interesting thing is that now you can derive other physiological measurements also for this type of daily patterns. So then geographically, you can see that these changes also happen in space. So it's not only in time. So here is for privacy. EU, we are very careful with privacy. So this is my own data. This is where I live, and this is where the university is. And this was a busy day where actually I had students doing this experiment 4, where people had to wear this whole equipment outside somewhere in the city center. So I had to go back and forth from the university back to where the students were collecting data. So I had this day where I did a lot of trips and activities using different modes. And I could see that, again, I'm plotting here just the heart rate, and you can see that the heart rate in activity where I was trying to get to my office with a long walk trip, then heart rate goes up. And I was worried that I saw a red dot in my own office, and to make sure that DTU, my university, is not getting me with a very high heart rate. I understood that was doing a change mode, not in my office actually, and that's why the heart rate went up. But this is the kind of data that you get. And of course, you can imagine that you can get these kind of things from commercial, eventually health equipment that you wear. Yes, Omar?
Sorry, just a clarification question, Carlos. In psychology, there's all this discussion about how to define an action or response and an activity, which is a kind of collection of responses, right? So from discrete responses to more long-term activities, right? So when you define something like walk, walk could be walking up the stairs in the metro, or walking on the sidewalk, or how do you measure these things? Like, how do you differentiate between them? And is there a reason for picking those in terms of what you're interested in, basically, or is there a literature on this, or?
Correct. So the definition used here are the definition that is commonly used for mobility patterns descriptions, which are different from if you go to the community that work on physiological data from the physical perspective, right? If you stand up, use clinical studies to see if people do more activities at home, for example, that can affect. So that's a different definitions. The way we define this, it's basically you compute for how long are you staying within a threshold to the same position. And so meaning that if I'm within a certain threshold, just walking in circles in a small, that will be in an activity. I'm not doing a trip. So it's from a mobility perspective, and there are ways to define this from the literature for the mobility spectrum. So of course, if we are looking at in-home activities, for example, or even in the office, if you are doing a very active activity within the office, like I'm presenting now standing up while sitting down, it has probably a different response. So then we cannot rely on the way we've defined it for our study.
I see. Thanks.
So this data is rich. So now, so what we can look at the data collected by everyone, right? And so here again is just first on the left-hand side, we can see the heart rate. And what you see here, it's again, the distribution of the heart rate for the different type of activities that were collected in the data in Copenhagen. And here on the y-axis, I don't know if you see my my mouse, but basically the right brackets with numbers on the y-axis on the right shows how many individuals had at least one of these activities, right? And so you can see that, of course, when you're walking or bicycle, your heart rate tends to go higher than in other transportation modes. But interestingly, we start to see that there are clear differentiations on the different activities that you do in the day, and also in terms of variability, right? And this, of course, starts to show a bit the richness of the data. There's nothing much we can extract from it directly with an interesting, or maybe there is, but for us and for the literature, there is a set of statistical measures that you extract from these physiological sensors that have shown to be associated with certain emotions or stress, right? So for example, it's more interesting to look at heart rate variability, for example. And there are ways on maybe different ways. So in the literature that shows, okay, can you compute these type of statistics that can be usually meaningful as proxies of stress? And so here the heart rate variability, it indicates usually like a strong vagal activity. So the parasympathetic kind of activity that is greater, and it suggests that usually the body can adapt quickly to internal and external senses, right? So interestingly for us, the conclusion is that here for the case in Denmark, driving, when people are driving compared to actually riding the bus, you have a greater heart rate variability, which, you know, if it would be in Portugal or in Italy, driving would be much more probably stressful than it is here. The same thing on the electrodermal activity. So the skin conductance and the sweating, you can again try to find recovery time. So recovery time, it's usually suggests more when you have a greater average recovery time, then it shows the potential for better emotional regulation. And here we saw that during social activities, you have a greater average recovery time. And when I mean greater, here it was a standard test for the distributions in 2 different types of activities. And then if we look at what people say they are feeling, so the subjective valence, individuals that are aged 50 years old or more have an overall greater median of subjective valence. And this is in the literature, that people that are older, they usually are happier in life on average, or in median for us in this case, which is good news for me. And the lower subjective valence, this is important. We did these surveys at the beginning where we checked for chronic stress, depression, and anxiety. And we noticed that people that have a higher ranking in chronic stress from the standard questionnaires that are used to flag and send people for their physicians to check if there is indeed problems of chronic stress. So this is just a survey. You have to then, of course, follow up if that's the case. But people that ranked higher in this survey, they show lower subjective valence compared to the rest of the subjects, which means that they don't experience the same positive emotions compared to others. So this is what we collected in our data set. And then looking spatially, you could see that, and moving a little bit faster, you could see clearly that, for example, in the train station, the central Copenhagen train station, people were much more tense than, for example, people that were visiting the zoo. But you can, of course, then start, this is related to activities, of course, what they are doing, but also it starts the question that, can we make a link between also the features that are available within a particular public space, and not only what they are doing. And we actually asked individuals, how much did the surrounding environment affect the way you felt, right? So here was something that allowed us to infer if potentially the reason was the environment or something else. We also asked in the smartphone app, when they had to answer these questions, to give us a reason why they were feeling this way with an open text. And so we did some natural language processing to extract content, something that we did with Sección, we're still working on, which is very interesting to see. Anyway, so this is how much does this data tell us about variability of experiences when you move around. So here a bit more technical work on, okay, so this is actually what you're showing, Carlos, is actually not emotions, you're showing statistics from the physiological data and the subjective data. So then we said, that's true, so what can we do with it? And what we tried first is, can we find measures of emotions from the wristband, which means the following. Are we able to predict just from the wristband data, which we have continuously for 24 hours, together with some questions that we ask like 3 times a day on how are you feeling, and then we have the subjective aspect of it. So can we combine these 2 data to predict the latent variable of emotions? Okay, and the idea to do this is that if you have a good model that is able to do this, then you can predict the latent emotion for these 24 hours, and not just for the time for example, where people are subjectively telling us that, oh, this is what I'm feeling right now. So what we did was we use a deep-seated clustering method that we proposed, where basically you do some filtering of the data, but we don't extract. So the key point is that we don't extract these statistics that we have to predefine as proxies as before, like the EDA recovery time or the variability of the heart rate, because you can actually have a lot of these statistics that you can extract by time period. And we wanted to basically put the whole signal into our autoencoder, extract these latent spaces of lower dimensions that combine all these sensors that the physiological wristband has, and then try to find a clustering method that, depending on this embedding space, this latent space, we can match what people are telling us through the subjective questions. So what it does is that, imagine that you have the sweating, so the EDA signal and the heart rate signal coming in, and we build this latent space that combines these all possible statistics that we don't predefine. We have to train them to find out that are better able to capture a cluster between what people say they are feeling at that particular moment. So we combine, it's a joint model where we have basically this, we have to identify this latent space. That's one problem. And the other problem is find the latent space that then matches what people are telling us they are feeling. So we have this joint model of an encoder-decoder, and so it's a sequence-to-sequence autoencoder together with a clustering algorithm. And what we did to test this approach was, instead of using our data, because we wanted to make sure that we have a model that is able to predict this, we use gold standard data sets from the neurosciences, where they have a very controlled environment, a very controlled stimulus, and they are able to know exactly what was the stimulus at a particular time. So this is a data set where you have a small number of subjects, and for example, people have to watch a video or doing particular type of activity that either stresses them or leaves them calm or makes them happy or makes them sad or scared. So you have, we train this model for these different 3 types of data sets that are used for developing emotion recognition, with the particular intention that we don't want to just be good at predict. We are able to use these subjective statements by individuals to make sure that we can do better. So we managed to do this reach this type of accuracies around 60 to 80%, depending on the type of stresses that we're able to get from these data sets, which is acceptable, I would say. Okay, so now can we explain emotions? So of course, I'm not talking, but now we are applying this model to the outdoor data set that we collected to be able to predict, again, these clusters of emotions for our outdoor data set. And here I'll talk about if we can explain emotions with the work with 2 gentlemen that I'm sure you guys know, which are up there in the pictures. So here it's with Angelo and Bastian from the University of Chile, where we try to then use this data set to predict with a hybrid model with structural equations, these latent arousal, latent valence for activities and trips. So imagine that you have one observation is one activity or one trip, and you have the attributes for that particular activity. You have the demographics or the characteristics of the particular subject. You also have the environmental features, if it is an activity for that particular location. So if there was a lot of trees, if there was a lot of shops in the area that were collected with a smartphone. And of course, we know if it was a trip, not an activity, then we also know the mode, or if the person was the driver, or how long it was the trip. And the idea here is that we build this hybrid model with a latent arousal, latent valence. And then we have measurements. And here we use measurements both from the physiological instrument and from the subjective instrument, and the questions that we say we ask the individuals about how they are feeling. And so here, Bastian was the one that did most of the modeling and all of the modeling. We extracted these features beforehand and selected them with an SVM to find out from all the possible physiological features we can extract from the heart rate. Which one should we use in the model? Because there were too many. So we first did some classification to find the ones more linked to the answers that people were giving. And then we were able Bastian was able to estimate the model. And so what does it give us at the end? So because the hybrid structure or the linear structure of the hybrid model, you can then look easily at how much is the beta estimate and the contribution on this left-hand side towards latent arousal. So how activated and how intense is your emotion, and the latent valence, which means how positive or negative is your emotion. So you can think about high happiness and high stress. They have both high arousal, but the high happiness, the thrill, for example, has a positive valence, while the stress has a negative valence. It's not a good feeling. And so here you can see the contribution in terms of weights using home as the baseline. As arousal and valence with different colors. And interesting things we can see is that, interestingly, when you have a transfer, you have a low arousal, maybe you have to wait, so you get chilled, not so much entertained. The greenery was very nice to see that it has an impact, especially for women and for people that have a chronic stress from the survey. So it has a positive valence, a positive effect on both these segments of the population. That social activities such as entertainment and eating out have a strong positive valence if your activities, and of course also a positive arousal. So these kind of things start to get very interesting because we can directly show the impact of what you do on how you're feeling, and measure and having these differences about how much better it is for an emotion perspective if you do A instead of B. What we are working now, and I'll speed up a bit, is how do you move from this model, which is first a linear model, which is great to see these initial results, but it doesn't look at all the sequence of events that happen during the day. So each activity is treated independently of what you did before. So we did some interesting master thesis with a student, Alicia. She's now back in the US. And what we tried to do here was using a generative model used in music. So this may be a bit too exotic, but basically what you have here is we consider that so in music, let me try to explain first the music process. So some of the models of generating music, and we took an interesting one from 2023, is each instrument is a track, and basically you build a graph that connects the different instruments in such a way that if the notes go up or the rhythm goes in a certain way, then the model learns to put the other instruments on notes that sound good or that are associated with the same kind of behavior. So this is interesting because then if you know that certain instruments are going dynamically in time and in their intensity in a certain direction, then you are able to build a fifth instrument that then will try to follow whatever behavior it should follow from what it has learned in previous data. Here for the music, it should be music that is trained with this. So the other instruments are learned how the notes should go up and down. For us, we just took the architecture of such a model where we consider each type of track would be a track for the emotions, a track for the activities, a track for the modes, and a track for the features of the locations, for example. Which means that if you have done this sequence of activities in the past, then this is how your emotions should flow. And so this kind of architecture is interesting because you can have this very large sequence of events and for intensities or features that you associate with each node. So now you build a graph where each node can have a vector of features that keep changing over time. And what you do now is basically you have, again, a kind of autoencoder that takes in the whole signal of time and emotions, location, duration, and activity. So big vector about what happened in the past. And it learns the relationships in time between all these tracks. And what the encoder, the autoencoder does is then it reconstructs it back, right? So you can train this first part of the model so that it's able to understand the dynamics between all what's going on from modes, activities, duration, locations, and emotion. And then what you do is, if you want to do prediction again, is that you hide, you create so if you are able to do this properly, then you are able to predict emotions correctly, but then you can build a second network, emotions correctly, your signals correctly, but then you can build a regression network where you hide one of the tracks that you use for doing predictions, right? And that's what we do here. So you hide the emotions, and that's the track that you want to predict from everything else that you can observe. And two things that I have to notice, because this master thesis was done before we had processed, and Bastian has done all his great work, we had to predict heart rate instead of emotions. And that was our predictor. And what we saw, so it's a different conclusions that you can see, but the model performed very interestingly. You could see again that when you are, for example, close to vegetation, then the heart rate would go down. When you are close to road transport activities that you are doing, the heart rate would go up. When you are around a lot of shops, you're probably doing some activity that is not going to get you exhausted. You're just looking around and shopping, and the heart rate would go down. And you could find from this feature importance map from the last regression neural network which kind of factors are predicting your track that you're trying to predict. And my final point is on how do emotions affect decision making. So here it's a bit still ongoing, but I can tell you a little bit about what we are trying to do. There's also a side work that we are starting together with the University of Chile and Bastian again, but that's just starting, so I don't have anything to say. But what I have to say here is what we did to our the people that wear the wristband and the smartphone app. The subjects, the sample from Lisbon, so the 89 subjects from Lisbon, we asked them actually to do a two-step task inside an MRI scanner. So a two-step task, if you're not familiar, it's something that the community from the neurosciences developed to plan how good of a planner the subject can be. So it basically evaluates if, when you are making decisions, if you are able to predict this transition of a sequence of decisions. So let me try to explain a bit better. It tries to find out how much of habitual behavior you do versus how you do goal-directed and some forecasting and planning behavior when you are making the choice. The way it works is that you are first asked to do that's why it's called two steps. In the first step, you have to make a choice between two figures, and there is a probability of going either to the brown or the purple. So you have, for example, a 70% chance to go to the brown if you choose the first picture, and a 30% chance to go to the brown if you choose the second feature. And again, if you choose the first one, then you have different probabilities. And then after you do this first step, you move to the second step, and then you have to make a choice again. And depending on how you choose in the second step, you get a reward. And of course, subjects are asked to maximize their rewards. And then the key question is, how good are you at learning these probabilities of moving from the step one towards the brown or the purple? And with this, you can measure how good people are in estimating these transition probabilities from the first step to the second step. And then you can do a model, and basically, like our colleagues back in Chile, they did the same thing for a particular task with transportation, but you can measure how much weight are people putting in the model-based versus the model-free behavior. And the interesting thing here is that we then split our subject into people that were put under stress and people that were just a control group without the stress. And the stress here, it is I would say the practice that have been done previously in this kind of studies, where people are asked, there they suddenly get a shock, a thermal shock, and they have to make the decision after they have this thermal shock. So it's kind of a physical stressor, but affects also the stress, the mental stress on how they have to make the choice. And what you would expect is that basically people that have been under stress, which is the A, they resort more to the habitual behavior than the ones that were not put under stress. So I don't have time to go over this. Maybe Omar, you have seen this before a few times, but basically that was what the data showed for us. What we are looking now is trying to find if, because then you can measure for each person how good of a planner they are from these kind of tasks. And the idea is to see if there's any influence from this, let's say, personal characteristic that the individual has on how they plan their mobility patterns. We asked through the smartphone app if they had planned the activities and how the day went as planned. So we are planning to do a model where we can hopefully show that there is a relationship on this personal attribute with what happens in real life in their mobility decisions. So final slide. So things that we are working now, it's trying to apply this model for emotion recognition to our outdoors. So the idea is that we are able to estimate by only asking a few questions to people with these wristbands, we are able to estimate clusters of emotions. And so we are applying this now to our outdoor activities. How do our emotions affect decision-making? And so this is related to what I just mentioned, plus some work that we are just relying on the data sets that from the mobility patterns that together with the University of Chile, we're trying to find out if the probabilities of choosing certain activities during the day or certain other travel-related behaviors have changed given that they were previously exposed to a stress event. There's, of course, relying on this type of data set is interesting to look at particular, let's say, contexts. So we had a student that showed that by looking at just the subjective measurements of valence and arousal, that people that had a certain attitude towards a given mode were more likely to have a better experience on the positive modes that they have attitudes for. So let's say that you have a positive attitude toward the car, they would statistically have better experiences when driving compared to the regular population. And this we saw across all 4 modes except for walk. And now we are debating to see how much of our conclusions are valid. And then we are working on other experiments, like this gentleman is my boss. And we have this type of data that, again, you can know a bit more. So the difficulty about what I showed in our data set is that it has a lot of work to able to exactly identify the stimulus of certain emotions. And so for that, we are still pushing for having as many outdoors and real life experiments as we want. But then, of course, we need to control a little bit more about the settings, the context, and the decisions that people can be exposed to. And so this is another experiment for the emotional cities where we collected lots of data of different neighborhoods where we ask people to where, and we know where they are walking, we know the activities on the brain, and we are now starting to look at the data to see what happened. So yeah, that's it. So we had all these slides that I've presented had some contributions from these folks in the slide, but so I want to thank them as well. And that's it from me.
Great. Thank you, Carlos. So now if anyone from the audience has a question, just please go on and turn on your camera if you want. So we're not too ready.
Well, I tend to take up all the questions, but if maybe the students or well, maybe I can start with one.
Yes.
Well, from your last slide, Carlos, I was wondering, yeah, you tried to manipulate I guess, how different or how much of an effect will being in different neighborhoods have on stress and other measures of emotion, right? But I don't think you have much variance in Denmark compared to other countries, right?
That's true. I would, as a non-Danish, I'm not gonna argue against that. No, but there is some interesting things because there is still some socioeconomic differences, maybe not as some other countries in the world, but there is some, especially locally, right? So both from the segment of the population, but also from the urban features that they have. And I can tell you an example. For example, the new development areas that they have. So this is reclaimed land, right? So land that they took from the sea. And that has been just developed in the last 10, 15 years. So all these buildings are new. The green areas are surprisingly are very low because those areas have canals all over the place. So you have blue spaces, not green spaces. And so there's a big contrast on the urban features where everything is new, the buildings are taller, no greenery, compared to places that are older, lower density, greeners, or places that have, I can tell you, much like suburban areas, low density and high density. So there is some variation. It's interesting that we also collected the data in Lisbon. So we hope that we could also compare what we see here against what they've collected over there.
Yeah, because I was thinking that, well, Santiago is one of the most pathological cities probably in that. On the east side, you have all the money, and then the center is kind of okay, but the rest, the outskirts and everything is completely different. It's a different world, basically. And I don't know how safe that would be to implement here, but it would be much more, sensible, I guess, to those measures. The other thing I was thinking, now that you were saying this about Denmark, is that in neuroscience, we know that some emotions such as pleasure or how much you like stuff can be extracted from low and high level features of the environment. So for example, you get a painting, a classic painting, right, from different classes or different painters. And you can then train a deep neural network model to extract those high and low level features and predict with high accuracy how much utility or how much people would like that particular painting. And then you can also look at correlates in the brain and everything. But I was wondering whether also some of the aspects of just, how places look, colors, contrast, is there or is there not a canal, or is the canal clean or dirty, stuff like that would help in this regard.
So, Omar, let me just ask, rephrase a bit so if I understood well. Could, for example, features that are extracted from the visual part,
exactly,
be able to tell us already a lot about how people will actually perceive and
yes. So you're using the features of the environment in virtual reality, or you make people walk.
That's what they did. Yeah. The only, I didn't work in that particular study. The only can go back. The only that's exactly what they did in the VR. So in the VR, what they did was basically change the texture of the buildings. So it was a white, or it was a white with a lot of texture. There was like how do you call it? Like mosaics in the buildings, or they put the trees that were green, or the trees that was in autumn, and they did the difference, or the trees without leaves. So they had these kind of features that were very controlled. Also the lighting, so that they played with the trees, the texture of the buildings, and the third one was lighting, on the street lighting. So that's the three things they've played around in experiments.
Okay, that was what I was thinking. Yeah.
But they didn't look too much at the emotions. They looked at navigation.
Navigation, yeah. Right.
But it's a good idea. Yep. You're muted, Bastian.
Sorry, any other question? So I guess I have one. So I think this may have raised some interest among policymakers or, I don't know, transport agencies. Have you heard something like, I think with this kind of experiments, you could test the effect of urban policies or things like that?
Yeah. Yes. There are, so far I got two different feedbacks. The feedback from the transportation agencies has been, okay, how much of these experiments could help us in designing the new stations, right? So there's a lot of interest from both the consultancies and companies that are developing the infrastructure. Maybe because the emotional cities were very related to urban spaces, right? So it was not so much about the whole transportation experience, was very local, you know. So there has been a lot of interest from that perspective, both from the transport operation, the consultants and architecture, how do you call it, ateliers or whatever, that want to design the new stations and start to rely on this type of experiments to collect information and to show that their theories are valid. Then you have the more recent feedback, which is also interesting, is the following. It's more from a transportation planning perspective, which is fine, you do all of this, but at the end of the day, we need a measure to include in our appraisal, cost-benefit analysis, whatever that is. And so it then raises the question on how much of these emotions and experiences that you are measuring are internalized in the choices or externalizes or externalities of the choices that you have to put some, you know, from an economical perspective, a money metric on it. So those are the two feedbacks. Because if you look at our transportation planning folks, at most what they have is, oh, if you drive and you switch to bike, then you do some activity and they have a factor on how much does it gain in terms of health, or if you switch from car to walk or public transportation, it means that you're saving from traffic accidents and they have a monetary value. Most of the time, these conversions are based on health gains, and most of the time the health gains are very basic as activities, cardiovascular, physical activity, sorry. And that's it. So the question is, if you bring in all these dimensions about experiences, then first there is the question on how much can you internalize. So basically how people already consider all of these when they are making choices, right? And then you just have to make sure that you have that mechanism in the models so that the choices that you are included in these models have this perspective. And if it's something that it's not included in the choice that you cannot internalize, then how do you put the money value? And here, my impression is you have to work back with the people that work on epidemiology, public health, and start to show how these studies that are clinical or more physical have to start to get into these more just record-based analysis where they come up with these numbers. Yeah, so those are the two feedbacks that I got so far. So what I mean is that if you see how these values are computed, right, often is you go to public statistics of healthcare and eventually compute stress, and you get the money value of stress from the public health sector, and somehow you try to so monetize this somehow. But there are a lot of things that then this can affect, right? Because for me, it's interesting. If you are stressed and you for some reason have one of these personality traits that affects you from getting out of the house, then you lose accessibility, right? So and then you start not doing activities or not taking the car or not doing A or B or C because you have this type of experience. So that's one interesting thing. The other interesting thing, of course, you want to, everyone is talking about changing behavior with climate or other agendas, and they evaluate the scenario from 20 years from now, but ignore the whole process on how to get there, right? So you say that we need to have 60% of the fleet by electric vehicles or whatever, but the process, behavior process, how people would experience to get to that point is affected by a bunch of things that somehow you have to start considering it when you do these forecasts. So the question is, in our community, when we do forecast, we do now and we do 10 years from now, whatever happens in between, we don't care. So I think we have to start understanding that when doing forecasts and do policy now, there will be an adjustment and learning process that you have to consider. And the learning process, often we do it in some waiting or whatever, but there is this whole thing that should be considered when you are doing these things.
Yeah, that's very interesting, Carlos. Sorry, can I ask one more question, Bastian?
Of course, yes.
Yeah. Can you go back, please, to the model-based, model-free task, Carlos? Because I was just wondering something about the results. Maybe I got it wrong, but.
Yep.
Okay, so if you read that paper from Bastian, you remember he found that not provoked stress, but self-reported stress from these psychometric questionnaires was associated with less model basedness. Basically, people got more model free as stress was higher.
Yeah, so you get more habitual behavior, right?
Exactly.
Yeah,
and
same here.
then you would explore less the new option in the third phase. Here, I think, first of all, so here what did you do to stress people out? Did you chalk them on the wrist, or I missed that part?
Ice, yeah, you have to plunge your hand in iced water.
The classic, yeah, that's the best one. Did you measure cortisol or anything, or did you just assume that they were stressed?
Yeah, they did. I don't think they used it in this first analysis. They did measure the cortisol, yes.
Okay, cool. But you also mentioned some other manipulation, right, Carlos? Like, in terms of stressing people out in the lab.
No, in this one was just the ice cold water.
Yeah. Okay, so here
that's this group here. That's the group A was the one that had to plunge their hands in the ice cold water, and B there was no stressor, and C is just both together.
The classic one, yeah. So then, when you say that the stress condition, there was an effect of reward in the stress condition, that means that they got more model free, right? Because they would just consider the previous.
Yes, you would expect, exactly, because you would expect that for the rare transition type, right? This would be
exactly.
If they would be exploring, then this would go down when they move from the first decision to the next one, right? So they wouldn't stick with the same decision as previously, but actually they do. So this should be, yeah.
Okay, so that's consistent with the notion that habitual behavior, appears with stress.
At least in our data, we're happy to see that it showed up. That was what we expected, and it showed up.
Yeah, that's cool. Yeah, and the last one, the significant effect of reward and types transition in the control condition is basically the main result without any manipulation, right?
Stress. Correct.
Okay, so all right.
Yeah, so that means that in the control condition, people are actually trying to estimate the transitions. Yes,
exactly. Yeah,
times reward.
All right. Thanks, Carlos.
Thank you.
Hi, Carlos. I have a question related to the sequence-to-sequence autoencoder model. Did you
Okay.
use the same data that you collected in experiment 3, or you use
Yes.
another?
Yes.
So the idea was to process the signal and learn the abstract representation of the signal during the
No,
object
no.
model.
So, okay. So if you are talking about this,
Yes.
okay. Here, no. Here, how we train the model, we train. So here we train each model for each person of each of these 3 different controlled experiments. So the VESA, the
Okay.
stress predict, and the CAP 300 VR. So this is 15, you have activities
Okay.
of
Yeah,
15 seconds of meditation, then you have to watch something, then you relax, and you have 30 minutes of observations for 15 people.
Okay.
And you have 3 types of stimulus. Then you have the stress predict has 2 types of stimulus, which is stress and non-stress only. And you are watching videos as well. And this one is a VR experiment where you also have 2 categories. And those are all open data sets. So we didn't collect it. They are out there.
Yeah.
And there are a bunch of papers on it.
Yeah. But
Or
my
at least,
question,
no?
have you tried using your data? Or because you have the signal, you can learn the representation and then try to understand the embedding, or
Yes.
across
Yes.
the city or across the mobility
Yeah.
patterns or something like that?
Yes. So we basically, so what we are doing, and I can tell you the results from last week. So what Marta did is a PhD student from the University of Medicine that is doing that. So she did this. It worked okay, and she's submitting the paper on the gold standard data sets. And then what she did is she kept the architecture that she learned from this exercise with these 3 data sets. And now she's training this model for each individual for the data sets that we collected outdoors. And she's doing it for the data set in Lisbon. And here the accuracy for her has been around between 60 and 70%. So a bit lower, or probably in the range of this data set here. And so the issue with this is that she's training it for data, which is for each person, almost 2 weeks of data. And so it takes it takes maybe 5 days or 6 days for each person to do one estimation. And then she's doing the crossfold, and she's, changing a bit some of the parameters to get it better.
Yeah.
And this is done for each subject, you have to train it separately.
Yeah, maybe a posterior analysis maybe could be interesting to just correlate the facility across the city with the embedding learned through the signal.
Yeah,
That would
I
be
see.
super interesting.
Yes, we need someone to do that. Gabriel.
We're working with Baxian with another idea, but yeah, open to that.
No, just kidding. But yeah, that's the whole point of her applying this model to this data set is then, right? Then you can go back to this stuff, right? Then you can go back to this. And instead of looking at heart rate, you have a probability of belonging to one of the clusters of emotions. And you can track the probability in the same resolution as she's developing the model, which is every 2 minutes. And there's literature that says that's usually between 1 and 4 minutes that you can have physiological data enough to predict the state of emotion. But here it depends, right? So that's if you go larger than that, then that's too messy in terms of emotions. If you do shorter than that, there's not enough data for you to extract the physiological measurements associated with what you're feeling. But then there's a lot of, they know more than I am. I mean, I'm the transportation guy, they are the neuroscientists, so they are looking at how to fine-tune these things to make sense.
Thank you.
So I think we run out of time. So thank you, Carlos, especially because I know it's very late now and it's Friday. So
that's okay.
Thank you for the presentation.
Sure. My pleasure, and nice to meet you all. Have a good Friday and a good weekend. Bye.
Bye, Carlos.
Bye.
Nice to meet you.
Bye.
Bye-bye.